Excellent. Thank you for your patience. Wow. All right. Hi, everybody. After that wonderful display that I'm sure inspired confidence in my ability to computer, package management unites us all. We're all here for this, right? Didn't run in the wrong room. You didn't sit in the wrong place watching that ridiculousness for the wrong talk. Cool. Okay. All right. So let me get my headset. I'm going to put this over here and then this over here, and can I just, whoa, that scrolls fast. All right. Hi, I'm Sam. I, by day, am a software engineer at Stripe. I also work on package management for Go. I also wrote an article about 2 years ago, almost like exactly 2 years ago. It was like February 11th, 2016. That was entitled, "So You Want to Write a Package Manager," and it was absurdly long. But that article, I had at the time, my goal was I wanted to work on package management for Go, because if you don't know, is anybody who uses Go in the room? All right, so you know that package management for Go has been like a giant trash fire for years. So we really needed to improve things. And there were a bunch of reasons that I embarked on writing this. It's like 14,000 word long article with lots of cute diagrams. Do people know this article? Like a couple. Cool. All right. Read it at some point or not. I tried to write it with enough sarcasm that you could actually get through 14,000 words. So it's kind of entertaining as you go. Yeah, my goal with it was I wanted to really sort of lay out kind of the whole problem, not just for Go necessarily, but say what really is package management and what are kind of the best practices and ideas there in a general sense. And certainly it was sort of tilted towards what I was thinking about with Go, but I wanted to work generally on it. And that spirit is really the same one as this this talk, this unites us all idea. And I want to talk about this title, right? So I give talks a fair bit, and I'm definitely let's get along when we can kind of guy. But this is one of the more kumbaya talk titles that I've given. But I want to tease it apart a little bit because I think there are actually 3 different ways that we can look at this title that are kind of interesting. So the first possible interpretation of unites us all is there's this kind of an American idiomatic thing, so please forgive that, but there's this sort of pseudo-intransitive use of the verb unite, which is definitely not an intransitive verb, but it's interesting because it kind of refers to an experience that a group of people sort of share, and this is kind of a common thread that can be a foundation for camaraderie and relationships, but the connotation is passive. It's not like we are actively brought together by something. It's more like, oh, we have this thing that we share, and it's kind of nice. If we put it in terms of, hey, we have this thing in common, then we actually are now using the verb to be, which of course is intransitive. But I think that there's a fair bit of shared experience when it comes to package management, which is important to think about. The obvious thing there is that we all, okay, raise your hand if you had the experience that package management is terrible and you want to rip your hair out and you just hate everything. Right, so you're all honest. Yeah, pretty much, because package management is the worst. That's why we're here. So everyone has this experience, certainly. It's the easy one to point to. There's nothing like being in a foxhole with someone to inspire camaraderie. There is also something bigger, though, when it comes to the shared experience with package management that I think is important, and it's because of the way that package management is deeply tied into the process of creating software and the difficulties of creating software and all of the different unknowns that we are trying to deal with. So there's one sort of sense of unites us all. The next one is the sort of more standard definition of unite, right? It actually brings us together. This is another idiom, the ties that bind, but the things that bring us together, the things that bind us together. So in this sense, I think that it's interesting to think about in the context of package management, because package management is the thing that mediates and defines the relationship between people who work on software systems, at least to the extent that, our interaction with other developers is defined by our interaction with their code. And let's not push that metaphor too far because it gets kind of weird. But at least at a basic level, a fair bit of the time I'm interacting with other people through the code that they have published, and I'm doing that in a way that's mediated by my package management tools. So an important boundary in modern programming languages is the boundary established by package managers. And this talk is going to be somewhat slanted towards language package management, but I am actively trying to move away from that and sort of generalize, as we'll see. I'll come back to that. But certainly, language communities are strongly defined by the package managers that they have. This is actually kind of why, if I'm being honest, I find the moniker the C++ community kind of confusing. To be completely clear, I have never written C++ in a serious way, so I don't really know how they would define that community. But not having any sort of consistent package management makes it difficult for me to understand sort of where the boundaries of a community sit. So the third sense, well, if this was the title of the talk, then it would be fine to talk about individual communities or individual package managers, but the title of the talk is in fact not Package Management Unites Small, Reasonably Uniform Groups into Larger Tribes. It is Unites Us All, which means that I really want to talk about what it means to really be looking at the problem of package management as a whole. And that's something, this is really kind of a reach even to say the problem of package management in the first place. We refer to package management, but it's not a problem domain in the same way that compilers are a problem domain. However, I think that it should be. I think that's an interesting thing that's kind of starting to emerge right now. But compilers exist independent of any individual language. There are techniques in compilers that you can see applied across different compilers regardless of the language that they're attached to. And I think that we would all be well served if we could bring package management as a problem domain to the point where we can talk about it independent of a particular language. I also think that, at least when we're talking about the analogy to compilers is apt because the way that I tend to think about at least language package managers, and to an extent system package managers, is the output of the language package manager is the input to the compiler. Compiler phase 0, if you will. So, this is the outline for the talk. This happens to me a weird amount where I picked the title months ago without really thinking about what was going to be in the talk, and then when I actually sat down to write the talk, I'm like, well, what do the words in the title mean? Which I just do because I love words, and then I started tearing it apart, and turned out that the whole talk is in these 3 different interpretations of the idea of package management uniting us all. So these are the 3 parts. Okay, let's talk about the first one, shared experiences. So 2 parts to this, right? We have the part that we know. Package management is one of the very few problems that is blessed with its very own kind of hell. I mean, really, how many other places, not just one circle of hell, but its whole own hell. The particular brand of hell, a lot of it has to do with what happens when there are shared dependencies in a system. We've got A and B, and both of them depend on C, and there is just a knockdown, drag-out fight between A and B as to what versions of C will work with both A and B. There's different words for that: shared dependencies, diamond dependencies, a lot of things. But that's one of the main things I think that people think about. It is not the only circle in dependency hell. There are circular dependencies and self-referential, other kinds of self-referential issues. There are, overly tight or overly loose version constraints that get you all sort of stuff that doesn't actually work. But my take is there's a lot of different circles. It's a mistake to focus on any one of them to the exclusion of the others, even though the diamond dependency, the shared dependency situation is probably the hottest one. Of course, the thing is that with most package managers, no matter which problem you're facing, you have two problems, because most of them, unless you're actually like the person who wrote the package manager, you're only like 60% sure that the problem that it's telling you about, or that you think that it's telling you about, is the actual problem that you have to deal with, because this domain is arcane and complex enough that maybe it's reporting an erroneous error or an ephemeral error, or maybe it's reporting an underlying error that actually, this is the surface version of it. When you solve that, something else will happen. The problems just sort of keep compounding. And this is, well, like I said, this first bit is about the shared experience of pain, right? We see this a lot in package managers. I am of the belief that it is because it's a complex domain, but maybe it's just because all of us who work on package managers are bad at writing software. I don't know. Either way, it's easy, I think, to look at the frustration of working with a package manager and to compare it to some imaginary ideal. Where we don't have any of the problems that we're running into, and get really frustrated and be like, package management is terrible. Why do I even need this? I'm just going to roll everything to a make file, and everybody can go F themselves. This is usually not the best way to go. And so this brings sort of the second shared experience, right? The thing that I think is harder to see for that. For the same reason that a fish doesn't really sort of know that it's in water. So I think it's important to keep in mind the role of package management in the inherently difficult process that is creating software, and what you're doing when you are working with a package manager. So when I think about the process of developing software, I'm not going to write everything top to bottom myself. I'm not that person. I don't think that person exists anymore. So I know that I'm going to have to rely on other people's code, and I know that that's going to bring some risk into the equation. Maybe they are just crazy people. Maybe they're going to pull the code out from under me. Maybe there's bugs hiding in there that aren't easy to know about. Maybe there's security holes hiding in there that aren't, that isn't easy to know about. But the thing that I'm counterbalancing against is I still need to ship something. And if I can't pull in the things that other people are working on, then I can't actually progress. I can't do my job. So given that the role of the package manager is to essentially be the thing that mediates between the rest of that deeply unknown, very risky world and what we are working on in front of us, it's unsurprising that we would see a fair number of complicated and annoying things coming in through our package manager. It is trying to organize a very chaotic space. So when I think about a good package manager, I have some basic rubrics that I apply, right? My sense is that given that the world of dependencies that are out there is chaotic and is hard to know how much we can trust it, the best approach to anything like that is experimentation. If I need to go and test out whether a dependency works well, then I want to be able to do that easily, and I want to be able to pull it out easily. I don't want this to be an arduous process just to perform my experiment to get at the underlying question of whether or not this code is any good or the maintainers are any good. And similarly, I don't want the process of doing this experiment to sort of push me out on a limb where it's really difficult for everyone else that I work with, or my build process, or whatever else, to make it very difficult to replicate my experiment. I want to be able to iterate quickly and flexibly and explore the crazy chaotic world of dependencies, but be insulated from it at the same time, and be able to rapidly push things through so that my experiments give me feedback fast. It's a very weird sort of, I think, balance of two conflicting forces at the same time, right? We want, on the one hand, something that lets us be fast and flexible, and on the other hand, something that is exceedingly reliable in terms of its outputs. Okay. Cool. That's part one. Part two. ties that bind. So it's important to talk about the goals of package management, right? The sort of high-level stuff. As with any software, like if we don't have a solid grasp on its foundational purpose, then it is way too easy to get lost in the minutia of the particular little problem we're trying to solve right in front of us. And there's a lot of those in package management. So discussing package management as like a risk management system, as I've been doing, that's kind of high level and hand wavy. I get it. For this part, I do want to make a sort of another high level assertion, which is modern package management is constitutive of communities. However, the argument for this emerges directly from not high level pitches, but the actual guts of package management. So if you were really annoyed at all the abstract hand wavy talk, you can wake up now, because I'm actually going to talk about like things. And we're going to start from the beginning. That is, what is a package? I don't actually have a terribly satisfying definition that I can put into a single sentence yet. I'm working on one. But what I do know is that the floor, the minimum possible number of different definitions, is at least the number of package managers that are out there and working on things. None of them are entirely the same. And even subtle differences in the way that these different package managers define their packages make them, deeply and surprisingly incompatible. So, given that degree of variance, let's just start super simple with this. Let's say that this box represents a package. So first and foremost, the package is a boundary line. It separates this packages from other packages. You can think of that a couple ways. In one sense, it means that wherever this package physically exists, it's going to be possible to retrieve like a tarball of it and just this discrete package. That's a distribution time boundary. In another sense, it strongly implies, although it does not actually entail, that any software to be compiled or interpreted using this package will likely incorporate at least the name of the package and the software that it generates. That is a boundary that we can see at sort of compile or execution time. Packages also impose rules on what they contain. So whether this is whatever sort of kind of software this is, there's going to be some amount of rule imposition on its contents. By rules, I mean these can be really simple and it will of course vary from system to system, but maybe we're going to require that some sort of metadata file must exist, like a package.json file for npm. Maybe we're going to mandate that the file layout must conform to a certain pattern. Perhaps it's because that's the pattern that the compiler or interpreter that's going to be looking at this package later on is expecting. Maybe we go even further. Maybe we say that the logical objects therein, the files, the classes, whatever it is, must conform to certain like linting or test passing rules, whatever. The thing is, so even if you have a system which is managing to gatekeep on the creation of packages to make sure that like the rules are followed, there's still going to be plenty of gray area in the space that is in the possible set of packages, and it'll be possible to make judgments about like what best practice are about construction of good packages versus bad. So we have some rules. If we can enforce them in a way that prevents totally invalid packages from existing, great, but there's still going to be a sort of gradation of package quality that's going to mean something specific to the package manager environment that it's in. The other major thing, I keep on going the wrong direction. So in addition to imposing rules on the logical guts of the package, packages also expose some kind of metadata. I mean, and the examples here like super simple, but we can say they expose author or maintainer information or dependencies and constraint information, right? Which versions of its dependencies it's allowed to work with. This is necessary for the functioning of the manager by and large. It's information that is sometimes presented in interfaces, who is the author maintainer, what website is associated with, and then there's more functional information like that the package manager may need to use in order to construct a dependency graph. All right. There's a big piece missing, of course, when we talk about packages that way. We can't just say that they're a name. Usually they are at least a two-tuple. They are a name and a version. Now, if we're going to say that they're a name and a version, then of course we also have to realize that, and forgive my horrible notation, that there's going to be families of packages that all share a name but have different versions. Maybe there is some ordering relationship that we can understand between these. There's a v1, a v2, a v3, or something like that. Or maybe there isn't. That's not, a generalized guarantee of the domain. But if we roll this up one level further, then we make it to the idea of the package universes. That is, a simple way to think about a package universe is it is the set of all packages at all versions that exist, more or less, that a tool can access. So, yay! However many exist in this universe. Saying, though, that it's the set of all is actually a problematic oversimplification, though. Like our own actual universe, only part of the package universe is going to be observable or reachable at any one time for any given tool. There are a few factors in this, right? Like the simplest one by far is, well, if we were to say that like the package universe is the set of all packages at all versions, then that would include packages that sit uniquely on like your laptop right now, and I can't reach that from my laptop. So clearly we're looking at least some subset of the total universe of packages that our package manager might be able to interact with. There's also, if we're thinking about a sort of a time component in our universe, then it's possible that at least in some kinds of package management universes, maybe some packages go away. Maybe they get moved, but either way, the time dimension matters. And then, yeah, the metaphor kind of breaks down, but so the way that you constitute the universe really matters. So for system package managers and most language packages, most systems, they have some kind of central or perhaps distributed registry or repository that actually is like the set of packages, right? I'm in a very weird case here, actually, because Go is the exception to this, more or less, simply because Go uses more or less FQDNs for its import paths, which mean that like the thing that is actually deciding the universe is DNS, not not some service that some people are running somewhere. But for the most part, if we're saying that there is a registry or repository that is out there which is capable of taking a name and mapping it to an actual like physical package object, as soon as we say that there's a registry, then we're going to accept that, well, maybe there's like one public registry or a couple of public registries. But then there's also going to be the possibility of private registries or maybe like ancillary additional public registries. Either way, the interaction of all these together ends up sort of creating a view into the larger universe, and your package management tool at any one time is going to have a view just into some particular slice of the universe. Oh, that's weird. That wasn't supposed to be on the slide. Oh, well. So, all right. That's weird. Why talk about all this, right? My original argument that I'm trying to make here is that these elements actually tell us something about how we constitute communities using package managers. So when I say constitute, what I really mean there is that package managers both define the boundaries of and the way that you participate in a community of software. The rules that they apply are the rules that you end up having to follow. They are effectively norms that people are expected to obey when they are creating packages. And because those rules are guidelines at the end of the day. Learning how to better obey those guidelines in a way that is less harmful to the rest of the ecosystem, that is more helpful to the other people in the ecosystem while still, serving your immediate purpose. Learning how to balance those kinds of concerns more or less ends up being the definition of being a good actor inside of the system. And you learn how to trust other people through whether or not they do a good job of following the best practices in those sort of gray edge cases that we seem to be constantly spending so much of our time in, or at least I do. Additionally, the package then also must be in a reachable part of the universe. So that slice of the universe that our tool can actually see, for us, is kind of the bounds of the community. I mean, prior to the advent of modern package management, there were different ways that I guess you just curl down tarballs all the time, and that was fine, and you were used to doing that, and you stuck it in a makefile, and it was cool. But once the automation of package management came into play, that's just not how we do things anymore, for the most part. So the package management tool's ability to reach something really sort of ends up, for most purposes, determining whether or not this thing is kind of in or out of the community. All right. I don't know why that was in there. One last binding tie. History. A little bit of a story. So, a few years ago, I started a deep dive down the rabbit hole that is proof and correctness in software. I have no CS background, so this turned out to be quite the trip. And I am still super much just a dilettante with all of this. I've never cranked out a TLA plus proof, or even written things in Eiffel or Idris. But I came to a question that I think is a pretty normal one for people who've been down this rabbit hole. Who here is familiar with, just software correctness in general and proofs and such and things that go on with it? Okay, yeah, it's a super fun, super weird rabbit hole, and it gets super confusing super quick. That's lots of supers there, but it's because you kind of come to this question here, right? Which is the title of this paper that the legendary Tony Hoare wrote. Because as soon as you start looking at the idea that, wait, it's possible in the first place to construct a proof that tells us that the software does what we think it does, there can't be bugs. There's this there's a great quote from Dijkstra about tests do not prove the absence of bugs in a program, only their presence. This is always sort of the space that you haven't explored yet with your tests is where all of the craziness and the risk is. And the only real thing that you can do to deal with that space is proof. So for a long time in earlier history of computer science and software engineering, it was believed that, well, of course, we were going to use mathematical proof in order to be sure that our systems were correct. And Tony Hoare, of course, won his Turing, at least in part, for Hoare logic. Which he wrote up in a paper in 1969, which is a precondition, postcondition sort of way of asserting that the state of a program is good. That's now been kind of codified into Eiffel that I mentioned before. Super interesting. Anyway, kind of getting off topic. But he wrote this paper in 96. He's like, all right, so I've worked on this for 20 years. And how is it that we built an entire software industry which seems to work despite the fact that we have only explored the tiniest little set of paths of the things that our programs could do, and it seems to be good enough. And it's weird. The answer to this question, basically, is software engineering. It's a super profoundly unsatisfying answer. There are a lot of way stations on this rabbit hole, and seriously, it's fun to jump down. But in some way, we've made software sufficiently for some interminably, infuriatingly imprecise definition of sufficient, reliable enough through the craft of software engineering itself, writing tests, doing incremental changes, modeling things, formally and informally, and then, crucially, bringing us back, isolation and modularity. Right? If you look back over the history of software, the idea of modularity has not always been a thing. It's so familiar to us now. It's, again, one of these sort of fish in water type of things. But prior to the advent of compilers and higher level languages, that could do fancy things like stitch files together. We didn't really have the capacity for modularity. So also in the 70s, there were sort of two major things that were happening. On the one hand, we had structured programming coming around. This was Dijkstra and Hoare and a couple of other people, but the basic argument there was we need to get away from go to and jump, and we want to move towards subroutines and blocks and loops, the sort of primitives that we are familiar with in a lot of modern programming today. And at the same time, there was also modular programming, which was sort of co-emergent with structured programming. The big things emphasized here were separation of concerns and information hiding. Now, for the most part, modules are not necessarily themselves functional objects. We could, again, there's a little rabbit hole with wait, what's the difference between a module and a function? Both of them hide information. I can't even say that modules aren't necessarily functional objects. For the most part, though, they are sets of functional objects. You can yell at me about standard ML later. It's totally fine. But the reason that all this matters, right, is because the presence of modules. John Regehr is a computer scientist at the University of Utah. The presence of modules, when they are organized well, it makes the total size of the software almost irrelevant. We can focus on just the little piece that we are actually working on. And if you look at this and you cross your eyes a little bit, it really starts to sound an awful lot like packaging as well. Packages are also generally non-functional objects. They're containers around functionality. The point here is to say that I'm trying to stitch it all back together to say we've got a whole lot of different logic that we drop into the bucket that is packages, and we have some rules that we sort of enforce on it from the top, right? But the last layer when it comes to actually defining what a package is in your system usually comes from figuring out what the relationship is between whatever your programming language or your whatever system you're packaging thinks of as a module, and then what you think of as a package. Usually it's either one-to-one or it's one package to n modules, but there are cases where there's n modules, one package to n modules, or one module to n packages. That's it. But this relationship ends up being one of the really, really crucial ones to understand, because it makes way more sense in general to think of packages and the relationship to a set type of object like a module than it does to an individual functional element like a function. Which is all to say that packaging sits at the intersection of humans and software, right? It's the spot where we have this handoff, this interchange from a module, which may have some functional aspects to it, to the thing that humans actually interact with. I'm not attaching my name to a module, but I am attaching my name to a package. And that's important because it's the package is the thing that gets distributed, that other humans are making decisions on the basis of, that is getting organized. All right, 19 minutes. Okay. Last section with this terrible Unbinding the Boundaries title. All right. I'm kind of already transitioning into it by having this general discussion about what constitutes packages, but I want to move beyond that to talk about some individual things that really do sort of span and kind of look towards the future a little bit. So I don't know, maybe I'm spoiling the panel at 5 o'clock, but we're at an interesting moment now, I think. For a long time, and certainly still in some places, relationship between folks who worked on different package managers and different distros on different languages was really fractious. It was not a friendly place to be. And the past few years have seemed to change. It's really heartening. But I was going to actually put did I put a slide in? No, I did not. Okay. Literally just this morning, Kat Marchand from NPM tweeted something about how NPM 5 which was released a year ago now, 9 months or something like that. A bunch of the design of NPM 5 was informed by the article that I wrote, and then how a bunch of things that I've worked on in depth have been informed by their experiences over on NPM. We have now this package community space, which if you were sitting in this room, you might be interested in checking out. There's a Discord chat that we have open. There's like 25 channels for discrete package managers in there. But the point is, this is not. We're getting away from this sort of fractious relationship. We're getting to the point where at least the people involved in this are interested in talking about like what are the fundamental parts of package management. And I am very interested in that question. And what I have come to is that one of the first things that we actually have to do is define a taxonomy of package management if we want to be able to grow this into some kind of compiler-esque, language-independent, system-independent domain. This means talking about what the objects are, which we've already done with packages a little bit, but talking about then what the different choices are and what the meaning of them are, and classifying the different systems that are out there. It seems to me that this is a prerequisite specifically because I've seen a lot of conversations now between people who work in different areas, and we don't have shared vocabulary. We sort of have to hash it out every time, and so many behaviors end up getting encoded slightly differently at slightly different parts in the process, and all of that turns into something that are just sort of assumptions for people that it's very difficult for us to tease it apart. So teasing it apart is kind of the first step. So here's an example of what a taxonomy might look like. To be clear, the taxonomy is mostly like a forward-looking project. If you're interested in that, talk to me because I really want to work on this. But system versus language. So I think Philippe actually talked about this morning too, so I'm curious how mine compare with his. But so when we think about system package managers, they usually aim to create combinatorially safe package universes, which is a really interesting property and also a really difficult thing to do because the possible combinations are, it's a combinatorial explosion. But that means, that we are going to publish a repository where we have tried to test at least a reasonable set of the combinations of software that are in that repository, because we want to insulate anyone who is working on our distro from the possibility of an unintended interaction between software that produces some crappy outcome. So that is generally not what folks who are using system package managers are trying to spend their time doing. This also has a social implication, which is that there is a finite group of trusted people who are responsible for populating the universes. Version constraints are also usually correct because they've actually been tested together. And also system package managers tend to encode more at the metadata level. I mean, realistically, you can play Sudoku with dpackage. It can be done. These are free. Package managers are almost pseudo-programming languages. They are pseudo-programming languages in many cases. And because system package managers are so interested in general in keeping the contents of the package opaque, they tend to encode more information at the metadata level. That's where they put stuff. By contrast, language package managers are usually ungated. There's no attempt at a combinatorial guarantee because that's literally no one's job. I'm a developer, I push a package. My job is to make sure that my package works according to the definitions that I have set out with all the dependencies that I may have. It is not my job to make sure that I work with all of my dependers. That's like their individual job. So we don't make the attempt. There's no attempt at a combinatorial guarantee. Version constraints then are usually optimistic because we want to say, well, I'm publishing this now, but maybe I leave it, and I don't want to say that my stuff only works with this current published version of my dependency. Maybe it'll work. It'll probably work. Semver's supposed to help with this. Hand wave. It'll probably work with future releases of it, at least within this range. So I'll leave that constraint open so that I don't create a pain in the butt for anybody who is using my software 3 years from now when a whole bunch of new versions of my dependency have been made and it's trying to reconcile with somebody else. Of course, overly open constraints end up meaning that you have things that don't actually work together all the time, so, problems. But because language package managers are actually very much about the details and the contents of those packages. Very often details may flow through from the contained packages symbols and be used in the work that the package manager does. Actually, I should not say very often. I should say it should happen more often. Contrast this to a system package manager where they're going to try to encode that as metadata as opposed to inspecting the actual contents of the package. Encode as metadata as in a maintainer decides that the package has some property and sets it as additional metadata. It's not inferred from any sort of analysis of what is in the package itself. Besides the system versus language distinction, the single most important thing in a package manager is whether you allow duplication of packages or not. This is far and away the most important. It is relevant for both system package managers and language package managers. Nix and NPM are two examples of package managers that duplicate. As in, when I say duplicate, what I mean is, our shared dependency issue again, right? We have A and B, and both of them depend on C. If you duplicate, then effectively A and B get their own copies of C. Everybody's happy. A and B don't have to agree on everything. Everybody just gets their own little play space, and it's fine, kind of. Most others don't. The benefit of this and the reason why it's an estimable goal is because you can avoid SAT. You can avoid Boolean satisfiability, which I'll come back to in just a second. The costs vary. In something like Nix, I read the cost as relatively low in Nix. What are we wasting? Disk space? Oh, buddy. But in a language package manager, it's trickier. What you often end up with is things like multiple. You end up with global state that gets duplicated, and if you have multiple instances of a package, both of which are trying to connect to a database, and they both create database singletons. Now we have two instances of things both talking to the database at the same time, and all of a sudden your app is super incorrect in very, very weird ways that you didn't realize at all because the package manager made a decision about duplicating this thing. So the question of whether duplication is safe or not is often really quite intertwined with the way that the language itself works. But the benefit of no SAT is huge, because this is the giant thing on the screen and also sitting in the middle of this problem. When I say SAT, who knows what I mean? Cool, okay. Boolean satisfiability, yay. It is the first of CARP's 21 NP complete problems. NP complete means ouch, or if you know big O notation, it's O to the N in general for the solving part, or just oh shit, that's fine as well. So Boolean satisfiability problems are, I'm way behind my notes. They are problems which take sets of Boolean propositions and try to work out a combination of values that actually satisfies all the requirements. It is a tremendously difficult problem to solve, at least generically, and there's a whole field of research dedicated to it. In fact, until about, I think it was 50s or 60s that CARP articulated Boolean satisfiability, and it wasn't until the late 90s that they figured out a technique that actually made it computationally feasible to solve anything more than the smallest trivial problem. But their other big costs from this tend to be that it is such a complex problem to work on in general that it's very, very difficult to reason about the answers that we get from SAT solvers. There have been plenty of cases where some really, I don't know about plenty, there have been at least some cases where some just wonderfully well-researched PhD thesis made some improvements to some SAT solver, and it appeared to work, and then 3 years later they figured out that none of the reasons why that wonderfully researched thesis thought that it was improving things were actually accurate, and all the PhDs just cry about it. So it's a very tricky domain to work in. There's very good reason to want to avoid SAT if you can. At the same time, so here's the thing that I'm engaged in right now. So despite SAT being a very nasty problem, it's also potentially very useful. That's the reason it's so nasty. Now, the reason that we end up at SAT is easy to explain if we're just looking at version numbers. There's a Russ Cox, the BDFL of Go, has a great post-up called Version SAT, which he wrote 15 months ago or so, in which he just lays out, like, yes, version satisfiability is NP complete. But we don't just have to be looking at version numbers. We can also encode like deeper language rules as things that we want to put in the constraint solver that get really tricky to solve otherwise. But we have the basic tension here between approaches, and this is something that Russ and I are going back and forth on right now, which is sort of a SAT as the problem versus SAT as a platform for working on things. So here's this thing. It's called Schaeffer's dichotomy. I've got 6 minutes. It's a really weird result. So Schaeffer's dichotomy tells us that all SAT problems are either NP or NP complete. There are a whole mess of complexity classes between those two, but no satisfiability problems fall into them. And we can know for certain that if a given satisfiability problem, Boolean satisfiability problem, can be expressed using a subset of Boolean relations, just which sort of forms of clauses are allowed, then it will always be in P. And so this is interesting because Russ, and he hasn't put this post out yet, but this, like, I expect this is going to be out in public in the next couple weeks, or soon in any case, has something that he's describing as minimal version selection. This approach is his attempt to sort of work on package management where we treat SAT as the problem to be avoided, more or less. So the basic preconditions are, and I'm not doing the full dive here, I don't have time, and like he's gonna have a write-up, but assume that Semver can adequately define compatibility within a major version. I know, big assumption. Certainly doesn't work for dynamically typed languages. Maybe works for statically typed ones. So assume Semver works. 2, if we only allow minimum versions to be specified. And 3, a mechanism exists to allow duplication, but only across major versions, meaning that we can have, like exactly one version in the 1.0 range, exactly one version in the 2.0 range. Then you can actually work it out where we're on the P side of Schaeffer. You can express it using within the restricted set of Boolean relations that's dictated by Schaeffer's dichotomy, which is super cool. It's really, really super cool. Like getting around SAT but still being able to do essentially what we need to do is very powerful. There's a lot of trade-offs that come with this, but no time now. Here is an alternative. These are not actually, like I say that Russ and I are going back and forth over this. We're going back and forth over a bunch of things related to Go package management. These two are not like directly in opposition necessarily. But this is something that I've been thinking about for a while, which is the idea that, well, version constraints, they cause unnecessary pain, both when they're loose and when they're too tight. And because even if a constraint was like good when you set it, over time they tend to age poorly, no matter what, which just means that versions aren't great. It shouldn't be a big surprise. They're a really, really compact representation of a whole giant pile of information. That they would not be the best approximation all of the time should surprise no one. But given that they are approximating a whole bunch of lower level information, all of the symbols that are exported by a system, maybe we could do better if instead of just looking at versions, we peek deeper at the logical relationship between packages. So I'm tentatively calling this shape analysis. A CS professor friend of mine tells me that this is actually most analogous to gradual typing. I have not really dug down this rabbit hole very far yet, but the essential idea is that instead of just saying, hey, A depends on B, let's look at the bits in A that depend on the bits in B. And if we know that A.foo references B.bar, it doesn't matter if it's a function or a value or whatever, we just know that there is a name reference to bar, then we can do a very simple inspection on B. We can look and see if part of its exported symbol set includes B and bar. And if it doesn't, we know it's not going to work for some languages which have, dynamic typing, or not dynamic typing, but like, dynamically exported symbols. Not so great. But this is why it's sort of the idea of the API shape analysis is that maybe it gets us close enough to doing most of the work that we end up only needing to use version constraints to sort of massage things at the end, instead of needing to use them to define the whole domain. And then people can do a lot less declaring of awkward version constraints, and we can instead be a little bit smarter about how we pair packages up. All right. It's the end. Thanks, everybody.
Next time.